So Marco Abbadini is going to talk about the algebraic structure of spaces of integrable functions.
Thank you. So this is the first piece of research I did at the beginning of my PhD, and it was inspired by a paper with by my supervisor Vincenzo Marra and Tomasz Krupa, the goal of which was to do an algebraic approach to measure theory. One of the reasons they were motivated to do this is to have the possibility to apply results such as that in varieties of algebras there are all free algebras, and so have some universal objects that appear also in the title. But let's recall something from measure theory, so that then we can go deeper in this. So measure space consists of three things: a set, sigma algebra of subsets of it, and a measure. Here we take measures valued in 0, infinity. An example is R with sigma algebra of Lebesgue measurable sets, and the Lebesgue measure, or you can take the Borel sets, which are the sigma algebra, the smallest sigma algebra that contains all open sets. Okay, and now an integral function. What is it? So when we have a measure space and a function from that space to R, we say that it's integrable if it is measurable, and the integral of the absolute value is finite. Okay. And L1 spaces are these things, so given such a measure space, L1 of mu is a set of all integrable functions. Okay, let's go back to the paper by Krupa and Marra. The idea here is to see the integral from an L1 space to R as a two-sorted algebra. Now, in a two-sorted algebra, we have two sets and a bunch of sorted interpretation of sorted function symbols. In this case, L1 mu is the content of one sort, and it has it's an algebra of its own, because it has some algebraic operations that we can define internal units. Also R is the other sort, and now the integral is the interpretation of a unary function symbol between the two sorts. Okay, but here then we might discuss, okay, what algebraic structure do we give to each of the two sorts? What algebraic structure can we define? For example, L1 mu, and here in this talk we will consider in particular the algebraic structure of this first sort. It has at least a vector space structure, because R has a vector space structure, and by applying pointwise this structure, we get a vector space structure of L1 of mu. So if I have for example, if I have two functions in L1, then also their sum pointwise will be in L1. Okay, but so in order not to have just an arbitrary algebraic structure, is there a canonical one? So we might ask, okay, what is the richest possible algebraic structure that is common to all these L1 spaces? Okay. And the investigation of this work is to find this richest algebraic structure common to this. And okay. So just a bit of definitions and an example. If I have two integrable functions, as I said before, their sum is still integrable, but for example, their pointwise product is not integrable. For example, yeah, if I take as a space the unit interval 0, 1, and a function that goes like this, if I choose this function well enough, it may be integrable, but its square might fail to be integrable. So we say that the sum preserves integrability, while the multiplication does not. So preserving integrability, roughly speaking, means that it returns integral function when applied to integrable functions. Formal definition: if I have a function tau from a power of r to r, the power can be of any cardinal. This preserves integrability if for every measure space and every tuple indexed by kappa of integrable functions, then applying this function to this tuple gives still an integrable function. Okay, so for example, the addition preserves integrability, and while the multiplication does not. And here is the program. So first we want to understand what are the operations that preserve integrability, just like the sum. We want to characterize them. And then we will search for a simple set of generators. And then we will look at the variety generated by this clone, and we wanted to see if there's a simple axiomatization. Okay. Okay. In the end, with this variety, what will it be? Well, it will be it will be a variety in the largest possible signature that we can endow L1 spaces with. It will be the smallest variety in this largest possible signature. Okay. So again, we'll look for the largest possible algebraic signature we can equip all L1 spaces with, and we'll look at the smallest variety in that signature in which all these L1 spaces lie. Okay. So, first question. Which functions preserve integrability? And I prove this characterization. A function tau. Let's see first the case of finitarity. A function tau preserves integrability if and only if it is measurable, Borel measurable, and sublinear. Okay. So here, Borel measurable means that the preimage of a Borel measurable set is Borel measurable, and sublinear means that the absolute value of the function is bounded above by a certain linear function in the following sense. It means that there are real numbers, lambda 1, lambda n, such that for any x, any tuple x in Rn, tau of x has an absolute value which is bounded by the sum of all lambda I times absolute value of xi. Okay? Or if you want to break this into local pieces, this means that the function is at most linear at infinity, is at most linear in a neighborhood of 0, and is bounded on bounded sets. Okay, let's see some examples. For example, all linear operations are Borel measurable and sublinear. So what I mean by linear operations, the addition, the scalar multiplication by any scalar, and the constant 0. These are all measurable and sublinear, and so they preserve integrability. And in other words, L1 is a vector space. If I define pointwise the structure of a vector space from the vector space structure R, it's all well defined. Okay, but the square function instead is Borel measurable but not sublinear. And because at infinity it grows more than linearly. And so this is reflected in the fact that it does not preserve integrability. If I have a function f which is integrable, then the square might fail to be integrable. For example, okay, this example here. You take an f which is big enough so that its square is not integrable, but small enough so that itself is integrable. Another example, let's say dual to it, is the square. The square is measurable, but not sublinear, because close to 0, it's not bounded by any integrable by any linear function. And this is reflected in the fact that it does not preserve integrability. Our counterexample here, we sort of do the dual thing. Instead of taking a big F, we take a big measure space, let's say 0, infinity, and we take a function, let's say 1, infinity. And we take a function which goes to infinity, which goes to 0, which is integrable, but its square is a bit bigger, and it becomes non-integrable. Okay. Max and mean are other measurable and sublinear functions, and so this gives to L1 mu a lattice structure by pointwise max and mean. The constant one is measurable, but it's not sublinear because, well, at 0 it is not 0. Okay, and this is reflected in the fact that the constant function 1 may fail to be integrable. For example, on R. Okay. Okay. There's a characterization also for any arity, for any cardinal kappa. A function preserves integrability if and only if it is measurable and sublinear. Here, by measurable, we mean, let's say, cylinder measurable, meaning that it is measurable with respect to the cylinder sigma algebra on R to the kappa. And the cylinder sigma algebra, or product sigma algebra, is the smallest, it's defined like the product topology. So the smallest sigma algebra that makes all projections measurable. So if you want, you take all projections, you take the preimage of the measurable sets, and then you generate the sigma algebra. When I will say measurable, I will always mean cylinder measurable. And anyway, on R to the kappa, where kappa is finite or countable, Borel measurable is the same as cylinder measurable. And here sublinear means a condition similar to what we have before. The only difference is that I have to pick finitely many distinct elements in kappa. Okay, let's see some example. Well, I wanted to say, let's take the countable. So this is in general not a well-defined operation on R because it might be infinite. But a slight modification gives a well-defined function on R, which takes a countable sequence y, x1, x2, and maps it to the supremum, well, not of xi, but each xi you take the minimum with y. And this is well-defined, it's measurable and sublinear, and so it preserves integrability. Okay. All right. Now, if you want to do, let's say, for example, probability, where maybe the measure space are not of infinite measure, well, you might consider this other property. So when a function preserves integrability over finite measure spaces, all the results would be will still hold if you require instead of over probability measure spaces. This means that whenever I have integrable functions over a measure space with finite measure, then applying tau gives still an integrable function. Okay. Right. And we have a similar characterization in this case. So a function preserves integrability over finite measure spaces if and only if it is cylinder measurable and subaffine. Now here we allow also a coefficient kappa that might be not 0. Okay, and in this case we allow, in certain sense, the function to be not bounded by a linear function in the neighborhood of 0. for example, the square root now is measurable but not subaffine, and so it preserves integrability over finite measure spaces. And 1 preserves integrability over finite measure spaces. Okay. So we have the characterization. Let's see if there's a convenient set of generators. All right. First of all these integrability preserving functions depend only on countably many coordinates. Okay. So we can ignore any cardinal bigger than the countable, Aleph 0. Okay, and here is a simple set of generators. So the infinite clone on R of functions that are measurable and sublinear is generated by all linear operations. So 0, the sum, and the scalar multiplication. Now, we don't have 1, but we have the truncation by 1, the unary operation that maps x to x with 1. And finally, the truncated countable supremum. These generate all measurable sublinear functions. So in a certain sense, our algebra will be algebras in this signature here. And there's a similar thing for integrability over finite measure spaces. So these the functions that are measurable and subaffine. This clone is generated by all the affine operations. So now we throw in also 1, which then will give you all constants, because you have also scalar multiplications. And then the truncated countable supreme. Okay, and finally, an axiomatization. Do we have an axiomatization for the variety generated by R, by this clone? So, okay, so now we are looking at the variety generated by the clone of measurable subaffine. Let's do first the case of finite measure, because the algebras are more similar to things that are known. So now we take the variety generated by the clone of measurable subaffine functions on R. This is a variety which is of interest because it contains all L1 mu space, all L1 spaces, and these can be identified with the class of Dedekind sigma complete vector lattices with a weak unit. Here a vector lattice, okay, which was kind of surprising to me because these are all well-studied concepts. And here a vector lattice is also known as space, is a vector space with a lattice order satisfying certain compatibility conditions. We have already seen yesterday vector lattices. A Dedekind sigma complete means, for example, R is an example. R is an example. Does not have all countable suprema, but it has all countable. It has suprema of all countable subsets which have an upper bound. Okay? And this is the definition of Dedekind sigma complete for a vector lattice. And finally, a weak unit is an element. Well, think, for example, up to the set of functions from I to R, a set I to R. 1 is a weak unit, the constant function. It's an element, positive element, denoted by 1, such that x inf, the minimum, so the inf between x and y equals 0 implies x equals 0. Okay, so we have a simple and familiar axiomatization of this variety. Right, so the structure of a Dedekind sigma complete vector lattice with weak unit is the smallest varieties in the richest possible algebraic structure concerning this L1 mu. Okay, and some a characterization similar obtains for the general case where we allow also infinite measure spaces. In these cases, we don't have anymore the weak unit, but we have a unary operation which behaves like a meet with a weak unit. And these These are called Dedekind sigma complete truncated vector lattices. Okay. Right? So in particular, as a consequence, these classes of Dedekind sigma complete vector lattices with weak unit, for example, is a variety of algebras. So it's generated by R, and it's generated by R. So they are all of the form H as P of R. But actually, we have also more, meaning that these quotients are not just arbitrary quotient, but they are quotient by a sigma ideal of the indexing set. So actually, every such algebra is a isomorphic to a subalgebra of a sigma reduced power of R, where sigma reduced means a sigma, you use a sigma ideal. Okay. And finally, is another consequence. We have that the free Dedekind sigma complete vector lattice with weak unit over any set exists. If you want the forgetful functor to set as a left adjoint, and we have a description of these free algebras, which is the set of measurable and subaffine functions from R to the I to R. And similarly, the free Dedekind sigma complete truncated vector lattice over any set exists. Again, because we have a variety of algebras, and is the set of measurable and sublinear functions from R to the I to R. Okay, in conclusion. Now, the L1 spaces lead to considering Dedekind sigma complete truncated vector lattices, and if we restrict to finite measures, we have Dedekind sigma complete vector lattices with weak unit. And we have a description for, well, the free algebras exist, and we have a description for them, which is in one case the set of measurable and sublinear functions, in the other case the set of measurable and subaffine functions. Okay, thank you very much.